Hello and welcome to level 314. Today we're going to work on the conclusion to our experiment on finding the curve on the supposedly flat Earth. And that's coming up right now. In part one of our exploration of the shape of the Earth, we developed a model and derived equations that helped us not only determine that the Earth was spherical, but to actually calculate the radius. Now, in that experiment, we came relatively close to the expected value. We were within 15%, but now we want to look at ways that maybe we can improve our results. So typically in scientific experiments like this, I like to think of three different broad areas where errors can creep in. And I call them the three M's. The first is in our modeling. Now, this is the most important. This is what we're trying to demonstrate the efficacy of. And if our model is wrong, we expect that all of our results will be wrong in the end. And then we have to go back and really analyze the model and improve it. Now, one of the main differences between science and pseudoscience is that we acknowledge when there are issues or limitations in our models, and we continuously work to improve them. So we're going to make some improvements to our models, but we'll come back to that in a minute. The second M is method. Now, what I mean by this is once you know your model, you have to come up with some method to go out and conduct the experiment in the world. And here we want to make sure that there aren't factors that we hadn't thought about that can affect the results of our experiment. For example, when we did our flight in Cape Cod, Massachusetts from the Knob, if you look closely at the video, you will see that, especially from altitude, there are mountains in the horizon. So this cuts off part of the sunset. Here I recommend that you use a tool called SunCalc, and I'll put a link in the description, that helps you determine the true path of the sun at either the sunrise or the sunset from your position on a given date. So that's the model and the method. Finally, there's measurement. And here what I mean are things like measuring the height accurately from the ground, or measuring the time accurately using a stopwatch, or in the case what we've done here is we've synchronized the video from different angles from both the ground and from the drone. So that means our time will be accurate up to 1/24th of a second because we're shooting at 24 frames per second. So we have our model, our method, and our measurement. These are our three M's. Let's go back and take a closer look at our model and see where we can refine that. So if we look back at our model from part one, we make an assumption. We assume that you'll make one observation from exactly ground level and the second observation from some height h, when in reality, both of your observations are at some height, because even if you're sitting or lying down on the ground, you're at some height, even if it's measured only in inches above the ground. So in reality, what we have is this observation here at H1 and another observation here, and we'll say that one is H2. So what we want to calculate in this new model are distances to the horizons. Okay, so you'll see this is one distance here to the horizon for H1, and then this is another distance here to the horizon for H2. In the end of the day, we want the difference between these two horizons. So if we call the distance to the horizon, let's say D1 for the first height and D2 for the second height, we want to calculate D2 minus D1. And we want to compare that to the full distance for a full revolution around our Earth. So we know that we can calculate the full revolution or the circumference using the formula 2 pi r. Right? So 2 pi r is the formula for getting the circumference of the circle. That would be one full revolution. And that ratio is equal to the ratio of how long it takes to make a full revolution. So again, if you remember from part 2, that ratio is t, or a measured time between the two events, sunrise or sunset, from the altitudes, and the number of seconds. We can call it s sub d, or just s. Okay, so the number of seconds in a day. We can solve this for r, and that's simply by multiplying both sides by r and inverting this fraction. So solving for r, we would have r is equal to s, the number of seconds in a day, over our measured time t, times d2 minus d1 over 2 pi. Okay? Now we just need to figure out what these d2 and d1 are. How do we figure out the distance to the horizon in terms of variables that we either already know or variables that we're solving for? If you look closely here, you'll see that we have two right triangles, and we'll just put one of them here, but it's obviously the same. Let me redraw that a little neater. Okay, so it's obviously the same for D1 and D2, so we'll just use D here. And this is R, and this is R plus H, which would be H1 or H2, of course. You may remember from the Pythagorean theorem of right triangles that a squared plus b squared equals c squared. In other words, the square of the two sides, the sum of the square of the two sides is equal to the square of the hypotenuse. And here, these are a and b, r and d are a and b, and r plus h is our hypotenuse. So we can just rewrite this with the Pythagorean theorem. R squared plus d squared is equal to r plus h squared. Okay, so trying to solve this now for d, we're going to have to go ahead and multiply this out. So r plus h squared is r squared plus 2rh plus h squared. And we notice we have an r squared here on both sides, so we can cancel those out. So this is d squared is equal to this. Let's go ahead and factor out an h here. D squared is equal to h times 2r plus h. Now here we're going to note that r is much, much greater than h. That means 2r is much, much greater than h. So that means we can say that 2r plus h is almost exactly equal to 2r. Leaving out that h creates almost no error, right? So to make the math simpler, we're going to make this simplification. And when we're doing this in our model, we want to note it, and we know that this is a limitation. Some error will creep in from this, but it's negligible. Okay, so if we replace this with 2r, we have, let's just do 2rh here, okay? We multiply the h back out, and that's equal to d squared. And now we just want to take the square root of both sides, 2rh. So now we know for D2 and D1, we can represent the D, or convert the D into this value, 2rh. This is a very good approximation of the distance to the horizon, as long as h is much, much smaller than our radius. And in this case, it definitely is. Let's just clean this up a little bit. Okay, so let's fill this back in. So we have r equal to s over t times the square root of 2rh1, or rather, excuse me, h2. We have to do our higher second measurement first, so that we have a positive number here, and this is all over 2 pi. Okay, here we're going to factor out the square root of r. So we have, this is equal to s over t, square root of, we'll just square root of r here, times square root of 2h2 minus the square root of 2h1 over 2 pi. And here we're going to divide both sides of the equation by the square root of r. So r divided by the square root of r is simply the square root of r. And here by dividing we get rid of that square root of r. So we have square root of 2h2 minus the square root of 2h1 over 2 pi. And now we just square both sides to get our final result. So squaring the square root of r gives us r, and this is equal to s, seconds in a day, over t, times the square root of 2h2 minus the square root of 2h1 all over 2 pi. And remember, we squared both sides, so we squared this. And there it is. We have our result. Now we have a new equation that we can use to calculate the radius of the spherical Earth using 2 measurements this time. And this is a better model. It's more reflective of our actual reality. So let's go ahead with this new model with a solid method and with good measurements and run this experiment again. Last time we did it with the sunset. On the East Coast it's a bit easier to do with the sunrise, so we're going to go ahead and do it with the sunrise this time and get our results and figure out where our model, our method, and our measurements are good and how close our number comes to the expected value of the radius of the Earth. So let's go flying.
So this was my first attempt to measure the radius using the sunrise in Atlantic City, New Jersey. At first I was set up on the other side of that Ferris wheel. Then I realized the sunrise was not directly east and would be blocked. So I ran down the boardwalk about half a mile with all my gear, only to discover I was still blocked by a jetty. There was also haze on the horizon. That tends to be more of a problem for sunrise experiments compared to sunset. This is caused partially by the temperature gradient and the lower dew point in the mornings. So while I did get some interesting video of the piers, I had to abort this attempt at the experiment. I'll let the tape run for a few seconds though, so you can see what the hazy sunrise looks like. My next opportunity to test the model was in Ocean City, Maryland. Here's our equation again. Remember, we need to measure height from both the ground and the drone. Getting an accurate measure of time is a bit tougher for sunrise. The change is not as dramatic as when the sun vanishes at sunset. What I do is start the clock back at home based on when the first pixels in the video are completely saturated. That's how we know the sun has peaked over the horizon. Then I stop the clock when the same event happens from the ground. Okay, I'll let you enjoy the sunrise and come back to summarize when we have our result. In the end, our hard work paid off. We were within 7% of the expected value. I encourage you to give this experiment a try yourself. Leave a comment below with your result or if you have ideas on how to improve the 3 M's. Like and subscribe for more content like this, and until we see each other again, keep taming irrationality bit by bit.